For the setup here, go to the lecture materials folder. You can find the link below in the notes. In there you can find folders for notes as well as Mathcad. And since we'll be doing the Mathcad, grab that file, download. Everything we're doing today should work, again, in Mathcad Express, the free version. You don't need a license for it. So that should work well for you. And then the notes as well as basically everything you're going to see in the slides with a little bit more text for explain things. We got an example here. We're going to do it quote unquote by hand. So we got our overall frame structure here. All right, a vertical and a horizontal piece. Our areas and moment inertials are given. We've got a distributed load across the top. We've got 80 inches vertically here, 100 inches horizontally. Modulus of 10 times 10 to the 6th psi. We want to find here is the displacements at each one of our nodes. All right. So here we go. Solution. So first, we need to discretize this thing and get it into our nodes and elements. So we got nodes here, node 1, node 2, node 3, and then element 1 and 2. Right? For pre-processing phase, we still determine the nodes and elements, so we've done that. And we also want to locate those, because we're going to need to know the theta, the angle, when we ultimately figure out what our transformation matrix is. So for element 1, we're going to say node I is 1, and node J is 2. And for element 2, we're going to say element 2 is I, and element 3 is J. Right, looking at the angles, if we're going from 2 to 3, then that's 0 degrees. If we're going from 1 to 2, then we have 9 degrees up like this. All right, so hopefully that makes sense at this point. So the frame element stiffness matrix in local coordinate system is what we had from before. So just putting it here again in front of you. And we're just going to substitute in for EI, or AE and over L. So for element 1, we have this as our resulting stiffness matrix. And for element 2, we have this. All right, so let's go see if we can get that in Mathcad. All right, so come over here. So we got 10 to the 6th for our modulus, area of 10 inches squared, 200 inches to the 4th, and a distributed load of 100 pounds per inch. Displacement. All right, so here we go. Here is our stiffness matrix, our local coordinate stiffness matrix in our local form. And actually, I think I call this now the element form, so let me update that. And save that there. And I'm going to just pause the video and I'll come back. I want to update these to all the new lingo that we're using here. Okay, so as we go here, we have our generic stiffness matrix, so let's plug in now. Well, we have our transformation matrix also. Again, generic transformation matrix, generic stiffness matrix. So let's go in here and solve for the stiffness matrices. See if I can zoom out here a little bit so we can see the whole page. There we go. All right, so for element 1, I'm going to put in our angle here. So for element 1, we said it was going to be 90 degrees. All right, so we get 1.571 radians. Again, I'm keeping units outside here because we're mixing radians with inches in the deflection. All right, so over here for the transformation matrix, we get A gets substituted in there, so it solves for that. And then we come down here and we solve for our global coordinate form of our element stiffness matrix. All right, so now in the future, the same thing as before with trusses. You can just do the transform version and just use it like we did with the transformation matrix. All right, so that's that, and we'll take it back to the slides to look at it here in just a bit. All right, so over here we have A is 0 degrees for element 2. All right, and we come up with 0. Oh, sorry, not 0. This matrix overall. Just a note here, notice what we got here. It's the identity matrix. All right, reason for that is we are 0, we are horizontal. So it ends up just being the identity matrix. The global coordinates are the same as the local coordinates. All right, so let's go back and check here. So element 1, we got 1.25. We don't have 1.25 here. Well, that's interesting. What do we got going on here? Oh, we got transform version. Where's the transform version? There we go. So there's 90 degrees for the transformation matrix, 0 degrees for element 2's transformation matrix. And so, yep, as I talked about, there's the identity matrix. All right, so to determine the global element stiffness matrices, we need to do the transformation matrix times the local stiffness matrix times the transform of the transformation matrix. And this is what I had already done. All right, so there's that 46,875. So here's that 46,875. All right, that looks good. 125, 125, 1,250,000 there. All right, and then we go down to element 2. It's going to be the same as the local version. So if we just compare those two, we don't actually have it up there, right? Because we already, it would have been right here, but we didn't find KL by itself. So, all right. Looks good. All right, so let's go back to the PowerPoint here. All right, so we're going to put the stiffness matrix all together to get our system stiffness matrix. And to do that, we have to go from, let's see here, so we have 3 nodes total, right? Node 1, 2, and 3. Each node has 3 degrees of freedom, so 3 times 3 is 9. So we need a 9 by 9. So you can see there on the right-hand side, we got our global deflections, right? 3 for each node. So up here in the upper left is between nodes 1 and 2, which is element 1. And in the bottom right, we'll have nodes 2 and 3 for element 2. All right, and you see all the addition that's happening there in the middle. All right, so let me, before we get on to the load matrix, let's hit this again. All right, so we'll slide down here, and let's look at it in the system form. So, all right, so we got to do trans 1. So again, we're going from a 6 by 6 into a 9 by 9. So we're going to need a 9 by 6. All right, so let's do 9 by. There we go, 9 by 6. All right, and we want to keep for nodes I and node J, they're both for 1 and then 2 for element 1. All right, and then we got a bunch of zeros. Unfortunately, I don't know of a better way. If you know of a better way, please put it in the comments to fill these things out with zeros to start. I do not know of one at this time. And that would be a great, once these things start getting real big, it would be convenient to know all those values. All right. There we go. And for element 2, same thing. We're going to need another. We'll just copy this guy, save ourselves some work. Can we get the whole thing? There we go. So I got the gray shading on the whole thing. You can copy it over. And what we can try to do here, we can insert above, insert row above, 2, 3, and then we'll delete these 3 rows down here. Delete row, delete row, delete row. And there now we've got node 2 and node 3, and we'll put zeros to all of node 1. Just kind of copied and pasted that row 2. Yep, there we go. Try that one. All right, so that looks good. And it equals. All right, so that is our global system form of both elements 1 and 2. And now we just need to add them up. So we do it down here, and we come up with this big matrix for our global stiffness matrix. All right, and now onto load matrices. All right, let's go back here now. All right, so load matrix, we have node 1, there's nothing happening there. At node 2, we have the horizontal piece that has the distributed load across. So there's omega, distributed load omega across the top of element 2. And element 2 is between nodes 2 and node 3. So if we look back to the beam presentation, we have the table that shows what the equivalent nodal loadings are for a load applied to the beam. And so for distributed load, it's negative omega L over 2 for the for the lateral loading, and negative omega L squared over 12 for the moment. Negative omega L squared, negative omega L over 2, sorry, for the lateral loading at node 3, and omega L squared over 12 for the rotation moment that's applied to node 3. All right, so now we put in here for our force actual values, calculated through, and we get the minus 5,000 pounds at both nodes, and a moment of 83,333 pound-inches. So we'll go back, make sure we can get that. So expand that section, so I already have that plugged in here. Set equals on that, so there's the 5,000 and the 83,333. All right, go back here. Ooh, boundary conditions, that's next. All right, so boundary conditions, what do we got? We got this guy's fixed. All right, and this guy's on a roller. So let's see what we got there. Ooh, it's fixed, so all the displacements at node 1 are all set equal to 0. This guy can roll, so it can rotate, and it can slide left to right. It just can't go laterally displaced, so that means the lateral displacement at node 3 is 0. All right, so if we apply those boundary conditions to our 9x9 setup, we end up with a 5x5 for a stiffness matrix, and then it has multiplied by the displacement matrix as well as our load matrix that's been reduced down. So let's go back and do that. We need to do our boundary conditions. All right, so let's see, we move down here. So apply the boundary conditions. Looks like I didn't quite get over the page there. So I have this already done. So again, we want to go from a 9x9 to a 5x5. So we need a 9x5. And we want to keep everything at node 2, and we want to keep almost everything at node 3. We want to keep the axial displacement at node 3, and we want to keep the rotation at node 3. But we do not want to keep the lateral displacement at node 3. So that's why those are zeros. All right. So if we apply the boundary condition to our stiffness matrix, we get down to a 5x5 there, and to the load matrix, get that down to a 5x5. All right. I think you know what's next here, right? We're going to solve this thing up. So solving up, we get some values there. Looks like 0.0576 inches for our two axial displacements at node 2 and node 3. For lateral displacement, we just have that at node 2, so negative 0.0043. And we got the rotation of 0.0014 and 0.0018 radians. Let's see if we can get that here in our solution phase. And hit equals, and voila, 0.0576, 0.0043, 0.0014, 0.0576, 0.018. All right, that looks great there. All right, so let's go back here. So I want to look at frames and ANSYS. Now, I'm not going to do this in this presentation. This will be in the next presentation. So we'll look at an example done in ANSYS. So check me out, or check out the presentations in ANSYS, and I'll see you there.